Today, finally, I want to talk about a specific type of architecture for sequence modeling, which is the sequence-to-sequence models. The previous week, when we made an introduction to the subject, we talked about different I/O types in sequence models. Remember, one-to-many, many-to-one. Many-to-many is actually the sequence-to-sequence problem itself. And in sequence modeling, this is the fundamental problem. You have a sequence, you are converting it to another sequence. For example, language, Google Translate. It's a sequence-to-sequence problem, but it doesn't have to necessarily be a translation. For example, chatbot is also a sequence-to-sequence problem. You provide a sequence, and the machine provides another sequence as an answer or a question, maybe. Okay? So that's why the literature of sequence modeling has these encoder-decoder architectures for sequence-to-sequence modeling. The earliest studies of these encoder-decoder architectures were used to phrase representations, learning phrase representations, like a chatbot or a machine translation. And actually, even today, most of the sequence models, even the transformers, are some sort of encoder-decoder models. So what is this encoder-decoder model? So simply, an encoder-decoder is a network with two recurrent neural networks, where one recurrent neural network is the encoder and the other recurrent neural network is a decoder. The first recurrent neural network encodes a sequence of symbols to a meaning, a fixed length vector, and the other one decodes the representation. So it is like, for example, you have an LSTM. Let me draw it because this drawing is not properly true, remember. So let's design a machine translation system. So, and sorry, this sometimes happens. LSTM 1, LSTM 2, kind of. So you feed a sentence to this. I am Erdem, kind of sentence, okay? And dot. We have 4 tokens here, 1, 2, 3, and the dot 4. When you unroll this in time, LSTM is like a recurrent neural network. It will be something like this, okay? And the last one will be the end of sentence. Imagine I first feed the inputs and I create hidden states. At the end of the sentence token, at the 4th sequence for this example, the final hidden and the self state vector will have gathered all the information of the input up to that moment, right? So this is like a context of the entire input sentence to me. Then I feed that context to the new LSTM, okay? And I feed as an input something constant, like the start of a sentence, kind of something, a vector. It outputs something. I feed the output to the next unrolling time. Next unrolling time, next unrolling time. You see Z. And at each step, LSTM creates an embedding, which is hopefully Ich bin Erdem, if it is from English to German. So you see, I have used an LSTM to which I fed the input sequence so that after the final token of the input sequence, which is the dot or end of sentence here, the hidden states or the self states of the LSTM, if this is an LSTM, if this is an RNN, only the hidden states, if this is a GRU, only the hidden states, or this LSTM, self states plus hidden states, were created as a total aggregation of the context of the sentence. So I have in between a latent representation. Then I start feeding it to the next LSTM and create a word, then get that word as an input to the next. So it's more like this, because this is a unrolled in time representation. I feed the same inputs and I let it evolve. And these outputs become the new sentence. This is the idea of an encoder, decoder, recurrent model for sequence-to-sequence models, guys. And this is one of the early studies. So this is the study that used LSTM, Suscaver and Vinyals, and this is an important study, guys. If you remember, in 2014 or 15, I guess you remember those days. You were university students, most probably, and undergraduate students. You are still university students. One day, Google Translate started working perfectly. Everybody was talking about it like 5 years ago. That was the day this Google team of Google, very, very famous guys, Suscaver, Vinyals, and Lee, they've come up with this model and they uploaded it to the Google Translate system. Actually, that system, that specific LSTM encoder, LSTM decoder was working perfect. But today, we have the transformer, which is working much better, which is again another model which was proposed by a team in Google. Okay, so this is the encoder-decoder model. For NLP, it is like you feed it to the encoder. At the end, you have an encoded representation as the hidden states of the recurrent encoder. And you feed that to the decoder, so you get the outputs. And at each time state of the output, you feed the current output of the decoder as an input to itself. So it is like something like this. So something like this. This is encoder-decoder designs for NLP. So how does it stop? Because it's feeding itself. At some point, it will create end of sentence. You naturally stop there. You don't create anything more. One of the important problems of this design was the cost-loss function. How to calculate loss for a translation, for example, in NLP. Because in signal processing problems like vision, we have the ground truth. In NLP, if this is machine translation, how can I check or provide a penalty for this output? Well, that's a complicated business and beyond the scope of this course. There are different metrics for it. And if you take DI, I don't know, IS, I guess, Tuğba course for text analytics, you can delve into this. I strongly recommend you learn about the evaluation matrix for NLP, which is beyond the scope of this course. So in the end, we have this design. Just like I said, encoder-decoder designs are kind of a trademark for NLP sequence-to-sequence problems. They create a flexibility. However, even this design has become quite primitive these days, because when you try to model the entire sentence as a part of a representation encoded here, which is the last hidden state of the RNN cell, when the sentence becomes too long, you put on too much on itself that you start to lose the meaning of the first words of the sentence. That's why they have different mechanisms to cope up with this problem, which is called the attention. And these are some advanced concepts which we'll not cover in this course, but they are the concepts of the sequence modeling course. They're the advanced modeling course, sequence modeling course, I lecture. So I strongly recommend that course if you're interested. And that was solved with Badano's attention. This Badano's paper is about how they solve the attention problem, etc. So I'm not going to delve into the attention problem. This was just a gentle introduction to what encoder-decoders are for NLP. So at this point, from now on, I think you have seen the fundamental architectures of deep neural networks. I say fundamental. For example, a transformer is a very important architecture, but it's not the fundamental architecture. Transformer is an architecture which is composed of the fundamental architectures of deep learning. So from now on, you are ready to analyze any architecture and understand it. Because in deep learning papers, you're going to realize that they have a figure, usually the first figure, explaining the architecture of the model. So you know convolutional layers, you know fully connected layers, you have embedding layers, you have LSTMs and recurrent neural networks, and you know what they are used for. So when you see a model, you'll be able to understand the the utilization purpose of that model. And we are going to do that. Starting with next week, we'll be going over different deep learning architectures from the last decade. I'm going to introduce them to you. So this is a type of an architecture to do this. It has these parts. Having understand them, you'll have a broader vision of what these deep learning architectures are all about, and you'll understand your architecture that you use in your projects better as well. Okay, any questions?